Okay, we have already seen some examples of using Gauss law, but when you want to use Gauss law, there are several tips you have to remember, and as long as you follow these tips, using Gauss law will be very simple and very convenient. The first thing is that you have to make a sketch of charge distribution. Some examples are shown at the bottom. Some of the charge distribution may be infinite featureless plane is two-dimensional case, and sometimes it may be like a cylinder or wire, which is a one-dimensional case, and sometimes it may be a point or some sphere, which we typically say it has a spherical symmetry. Okay, and then try to find the simplest symmetry of the distribution and its effect on electric field. Okay, the first case was the planar symmetry, so which means that assuming it's infinitely long, the electric field will be the same wherever you are. If the size is not very long, electric field will be different if between the case when you are close to the center or close to the edge. But it is large enough so that you can assume that it is infinite, then it doesn't really matter whether you move sideways or not. Okay, that's what we mean by the translational planar symmetry. And as a result, you can easily guess that electric field will be coming perpendicular from this plate, and is also going up and down, right? Okay, so and then how about the second case? In this case, there will be a rotational symmetry. So if you go around this wire, then electric field will look exactly the same. And also if it's infinitely long, and then if you go up or down, it will be the same. Okay, that's the symmetry you have to find. And then the third case, a spherical symmetry. In this case, as long as you keep the distance from the center, if you make a rotation, everything is the same. This is called a spherical symmetry. And once you can find such symmetries, things will become easy. And then you will have to find any surface. Basically, Gauss law is true for any closed surface. So what you have to do is find the simplest case so that you can do the calculation as easy as possible. And remember, you are making a dot product between the electric field vector and the area vector. So therefore, there are two possible cases which makes the calculation simple. One is the case when these two vectors are parallel, then you don't have to worry about vector. It now becomes simply scalar because their angle is 0. And the other case is if their angle is 0, if the angle is 90 degree, then their dot product becomes 0. And then you will see how easy the calculation it becomes, right? So these are some examples. If you, in the case of this two-dimensional case, if you take the Gaussian surface to be a box like this, and then on the top and bottom surface, now dot product will become simply a scalar multiplication, and then on the sides, on the perpendicular side or vertical side, the electric field will be going this way, so therefore the area vector is 90 degrees, so now flux becomes 0, okay? And then how about the second case? Second case, so shape like this. Shape like this will be always the best choice. And then for the spherical case, of course, naturally, the Gaussian surface has to be sphere with this charge distribution located at the center. And then, finally, use the Gauss law to determine the electric field vector. Okay, so let's try some examples of using Gauss law to find electric fields. In the first example, assume that we have an infinitely large non-conducting or insulating sheet uniformly charged with the charge density sigma. Okay, this is shown in the figures on the right side. Okay, and in this case, one of the most appropriate Gaussian surfaces is actually a cylinder with its axis located perpendicular to the sheet, as shown here. Okay, Well, in the previous page, we tried a box-shaped Gaussian surface. Well, it's also okay. It doesn't really matter because in this case, the shape of the sidewall doesn't really matter. So therefore, you can certainly try the box shape, but here we will try the cylindrical shape. Here, the first thing to consider is that it's already drawn here, but the electric fields from this sheet will be going exactly perpendicular to the sheet, and the strength will be actually the same on both sides of the sheet. So it will be minus E on the left hand side and plus E on the right hand side because of the symmetry, but the strength, there is no reason why the strength will be different on both sides. Okay, so if you choose the Gaussian surface to be cylindrical shape, now you can think about it as a collection of three different surfaces. The S1 on the right side, the top of the cylinder, and then the S2, we call the S2 to be the rounded sidewall of the cylinder, and S3 will be the other side of the cylinder. Okay, and then so therefore what we are doing is that we are doing an integration of the electric field over the entire surface. Doing it over the entire surface means that we can divide into three different surfaces and then finally combine. So, and then another important thing is that on S1 and S3, remember that the direction of the electric field is actually parallel to the direction of the area vectors. So therefore, you don't have to think about the angle. This is just 0 degrees. So therefore, E vector dot producted by dA vector will simply become EA. Here, A is actually the area. So in this case, I will show it. This area, okay, this is what we call A. So therefore, on the for the S3, it's actually the same area. It's a right-angled cylinder. And then on the S2, why is it 0? Because in the S2, anywhere on the S2, the area vector goes this direction, but you see that the electric field always goes sideways, so therefore it's actually 90 degrees. So therefore the dot product will become 0. Okay, and then if you add them, you finally get twice of E multiplied by A, and this epsilon naught is there as a proportionality constant, and this will be equal to the Q inc, which means short for enclosed. And how much charge is enclosed here? We already said that the charge density is sigma, and sigma is the charge divided by the area. So therefore, the amount of charge inside the cylinder will be equal to the sigma multiplied by this area here. This is where the charges are. So therefore, you can finally say it is equal to sigma A. And then now A drops, okay, right? On both sides, now A drops. And finally, if you summarize it, now E is equal to sigma divided by 2E0. Okay, here, there's one important thing you have to realize. In this case, E does not depend on the distance from the sheet. Now, why is it? Actually, think about it. If you make this Gaussian surface much elongated like this, does the calculation change? Actually, nothing's changing because the sidewall doesn't matter. So therefore, the length of the Gaussian surface didn't matter. So therefore, the position does not matter. So which means the electric field does not really matter the distance from the sheet. And then actually the reason is because we have assumed that this sheet is infinitely large. So if it's infinitely large, actually moving slightly away from it doesn't really matter. Okay. And let's try the second example. Now in this case, this material is conductor and a charged conductor, right? So inside the conductor, remember, charges can easily move. So later we will have some chance to see it a little bit more detailed. But right now, I will assert, meaning that I will just say that all charges in conductor on the surfaces, and the reason is because they are pushing away each other by the Coulomb force, so they want to be as far away as possible from the other positive charges. So therefore, eventually, they all collect on the surface. So therefore, it will be very useful later if you remember that inside a conductor, all the charges are on the surface, and the electric field inside is always zero. Okay, I will say electric field inside zero. This is a common knowledge that electric field inside a conductor is zero, even though it is charged on the surface. Okay, and in this situation, what we want to know is that, okay, how much or how large is the electric field outside here? Okay, this is where we want to know the electric field. Okay, and then here we are assuming another thing. Here we cannot really think about infinitely large plate. So therefore, instead of thinking about the conductor to be infinitely large, we are assuming that we are very close to the surface. So if you are very close to the surface, effectively the area close to it will become very large. So therefore, we are thinking about the electric field right outside the conductor. And then again, now if you are very close, this small piece of area will look almost flat. So we can draw the figure this way. And then again, we are thinking about a Gaussian surface, which actually looks the same as in the previous case of the insulator. And then again, we are applying the same Gauss law and repeat the same calculation. And all the calculation look the same except here. Except here on S3 here. The electric flux is zero. Why? Because we just said that electric field inside the conductor is zero. Okay, but then the situation, if you think that the charge density on the surface is still sigma, then finally the amount of charge enclosed inside this Gaussian surface will still be the same. And then what has changed? Actually, you see that here, there's no 2. Above there was 2, but here, there's no 2. So therefore, finally, if you summarize it, the electric field right outside the conductor will become sigma divided by epsilon naught, which is in fact twice of the electric field next to the charged insulating sheet. Okay, these are the two examples how you apply the Gauss law. And before we end, let me quickly show you another example, which is the infinitely long wire, actually the insulating wire charged with linear charge density lambda. So lambda will be charge divided by the length. So in this case, let's again try to use the Gauss law. And then we have already said that the best Gaussian surface is actually a cylinder looking like this. Okay, so it's exactly symmetrically surrounding the Gaussian, surrounding the charged wire. And then in fact, we have this cylinder to have the height h, but you will eventually see that this height h doesn't really matter. And then let's try the Gauss law again. Okay, so we are again dividing this cylinder into S1, S2, and S3. As you can see that from this wire, because of the symmetry, the electric field will always point perpendicular to the wire. See that? Because it's wherever you are, there will be exactly the same amount of charge up or down. So therefore, there is no reason why electric field will be pointing, say, this direction. It doesn't go this way. It's always be perpendicular to the wire. So as a result, you can easily see that along S1, if you make a dot product between the area vector and then the electric field vector, it will become 0. And same is true for S3. And only along S2, the electric field vector and then the area vector will always be parallel to each other. So in this case, okay, let's try to use the Gauss law again. Okay, and then again we said that for S1 it will be 0, S3 again 0. we have to integrate only over the S2, right? And over the S2, now these are parallel, so therefore it's no longer a vector. And then you can see that if you keep the distance r from the wire, the electric field will be constant. So let's take the constant out. And then what you only have to do finally is simply integrating over the surface of S2. And what is the surface area of S2? Is of course 2 pi r multiplied by the height h, right? Okay. And then according to Gauss law, this is equal to the charge enclosed inside this Gaussian surface. And then we said the charge density is lambda. Lambda will be the charge q divided by any length, in this case h. So therefore, instead of q, we can write lambda h. And finally, here, using the same logic, the h drops from both sides. So therefore, E will be lambda divided by 2 pi epsilon naught r. And here, what is important is that you have a r. Okay, so we can say that this is proportional to the distance, not just the distance itself, actually the inverse of the distance, which means that if you are far away, the electric field will become 0, and then the graph of electric field as a function of distance will look like this. Okay. So let's make a final summary of today's long lecture. From this lecture, you have learned the definition of electric field and how to draw and read electric field lines. And you have learned how to calculate an electric field due to a point charge or distributed charges. And you also learned what an electric dipole is and how to define it, and how to calculate the potential energy of a dipole in a uniform electric field. And then you learned what electric flux and Gaussian surfaces are. And finally, we learned how to use the Gauss law to calculate an electric field. If you do not remember any of these, please go back and review the lecture anytime you want. And these are the things we are going to study in the next online lecture. But we will see you before the online lecture in the classroom on Thursday. Okay, I will see you there. Thank you.